Well, hello and welcome to a short presentation, probably about 90 minutes or so. It's a re-recording of a presentation made to Wars of the Future Partnership by CS Conservation Survey at Nottingham Trent University on the 20th September 2022. Now this pretty background here is purely to show that we also like pretty pictures. It will mean rather more to you in a minute, I hope. The lesson, or the lessons, the talk is subtitled Lessons and Limits. I think this is the most immediately relevant outcomes of the project. We learned a lot, as did Moores for the Future Partnership, and so did, I think, did Blue Sky, one of our suppliers. And we hope to pass these lessons on and hopefully save you from rediscovering them yourself. This was a 4-year project using UAVs, MAVs, satellite optical imagery, experimental use of thermal data derived from UAV flights, and an exploration of detecting change in erosion deposition using high resolution UAV derived DEMs. A lot of acronyms in there, isn't there? And I nearly forgot, over 7,000 field samples. The report itself runs to over 230 pages, and it's got more figures, tables, pictures and things that you could shake a stick at. So we aren't going to cover all of that. I've certainly no intention of boring you. Well, I probably will do, but I'm not going to bore you with the minutiae of, say, ortho-correction accuracies for all the images, for example. So if you want all the details, you will need to read the report. That's kind of the way it goes. Instead, I hope to cover the parts that lead directly to the main conclusions. More to the background of the thinking and planning behind the project, if you like. More about the why, rather than the what was done. I'm also going to lay out the chief errors and experiences we made. We've no desire to conceal anything. It's only possible to learn and move forward from others' experiences if you're allowed to see them all, not to have them hidden round the back to make the front all pretty and shiny. Okay, well, if in case you're wondering what the devil's doing here, well, corny or not, the devil's in the detail of this project, and there's a lot of detail in it. In effect, yes, this is essentially a simple project to map upland vegetation, but it's in the details of the execution and the deep implications, the results and outcomes that are really rather less obvious. To some extent, to make this clear, I'll also go through the story in a temporal manner, phase 1, then phase 2, etc. I think it will make it easy to see how the project developed and how we changed things through time. Yeah, and if anybody knows why the devil needs a little brush, please let us know. There's bound to be a lot of acronyms in here. I'm sorry about that. It's the nature of remote sensing. Well, much of science, I suppose. The most obvious ones here are EO, MAV, UAV. There's a personal note. I also tend to just bandy around the terms accuracy assessment and error assessment at random. They're essentially referring to the same thing. The numbers are the same too. So really, accuracy assessment equals error assessment as far as I'm concerned. I just don't seem to be able to decide on one term and stick to it. Thanks to Tier and Dermot, but also to their team members and volunteers, especially those who helped with a monumental amount of field work. Blue Sky were a commercial supplier, but I'm thanking them here because we took them, I think, well above and beyond the usual. We both learned a lot, and thanks to them as well for helping. Really briefly here, the project specifications were contained in 7 packages under 3 main headings. These were to monitor changes in land cover, especially sphagnum and bare peat, monitor surface wetness and rates of accumulation and erosion. The former was effectively the main component, and the latter 2 rather more speculative and experimental. There's also an initial assumption on the use of UAVs, and we'll have rather more of that later. Now, beyond that, we actually put another constraint on the project, and it was that we were going to carry it out in what we would call an operationally realistic manner. By that I mean one that would serve as a pragmatic test of techniques relevant to other agencies and NGOs. I.e. those that would not have unlimited access to specialist staff, computer resources, etc., etc. So what we did do was to use standard algorithms running on Windows PC-based GIS and MEMSEN software. We used ARC, and I'm sure you could use QGIS as well, or as an alternative rather, for the vector stuff, and we also used Erdas Imagine. Now if you're going to do this sort of work, you've got to invest something, and this is kind of a minimum suite. We also of course have things like Excel, Access and such like. For the UAV usage, we also use Pix4D for auto-correction, but anybody using UAV will need similar. Now what we did not do was to repeatedly tweak and retweak single images for months on end to eke out the last decimal place of accuracy. Neither did we develop any bespoke code or use esoteric machine learning approaches. These are all typical of an academic kind of research paper, where the primary idea is to show how clever you are, rather than have any real world application. And yeah, I can't be doing with that anymore. This project then was designed to be as real world as possible, and we think the results represent what ought to be possible in-house. At this point I feel I should stress we are absolutely more than happy for you to pay us to do it if you wish. However, all that said, one thing was crucial to us. We retained full academic rigour in our approaches, no ignoring this or changing that obviously, but especially key was a full statistical accuracy assessment of all the results we achieved. Now apologies to David Ockney here, but central to this is the adage that without accuracy assessment, remote sensing is nothing more than a pretty picture. It is something every remote sensing student at Cranfield used to hear over and over again at the beginning of their course, and why behind any of them used to hand in an assignment without such an assessment. There are already endless unsubstantiated claims out there in the grain sales literature and websites, all showing pretty pictures, but containing absolutely no data, and particularly no evidence to support the claims. This project was not going to add to these. Okay, I'm going to deal first with the main part of the project. This was the use of optical imagery to map vegetation and bare peat to determine if this could be used to examine change over time. We used UAVs, well that's in the title, so I don't expect you to be surprised by that. But indeed the contract is originally specified to solely use imagery from UAVs flown by MFFP. But the project broadened to use MAV data, bespoke capture by Blue Sky as I mentioned, as well as archive imagery from Worldview 2 for the study area. Now all classification, bar something we'll get to at the end, was executed using maximum lick or max-lick supervised classification in Erdas. Now this is pretty much bog standard as it comes. It's resource light and it's ideal for use in-house for NGOs, etc. It's really kind of familiar and easy to understand to anyone with remote sensing training, and for those of you who don't, well, I'm going to do a brief 1-minute remote sensing course in a minute. Please note, during the early phases of this project, tests were executed to compare results to other options. And really, not unsurprisingly to us, max lick was as good, if not better, than most more esoteric approaches, and hence we kind of stuck with it all the way through. Now, we did test a much more complex machine learning approach, and again it was no better, but Ben will expand on that later. Now, some of you may have heard of or used object or vector-based classification approaches, such as those in algorithms in e-cognition, and also Erdas. Well, these were excluded on many grounds, and we're happy to explain why if asked later. An approach has no application here. Okay, I tend to feel what we found out is probably more interesting than where we found out, so we'll be quick here as well. 5 survey sites, summing to 11 square kilometres. Within these were MFFP experimental catchments. There are also a lot more data capture going on in there, water quality and such like. You'll need to ask them for the results from these areas. Now, a picture's worth 1,000 words, I have once heard somebody say. I'm sure you all know where the Peak District is, well I hope you do. The study sites were all in the South Pennines Moor SAC. We had Mossmoor in the north part and Kinder in the south, and in between Howden, Penguins and Birch and Lee. Okay, now every project starts with a set of decisions, planning meetings and heaven knows what. And a key one here was the choice of typology. Now, if any of you are familiar with the term, a typology is simply the units or the classes that you choose to map. Now, it's absolutely fundamental to your project, and yet we often see it seems to be only cursorily considered. and not many of you may see why it's immediately so crucial, but this choice underpinned the whole 4 years of the project and every result here. And I also got a feeling that some of you may question what we attempted, so I'd like to spend a few minutes to background this. So it should be obvious that if you want to measure change through time, we need a typology composed of classes that everyone will agree on when they see them or see it in the field, every time, everywhere. We call this repeatable. Now, I cannot stress this enough. If a typology doesn't satisfy this most basic criteria, we cannot identify actual change from differences in opinions of different surveyors, and you're wasting your time and money trying to undertake remote sensing using such an approach. Now, it's become common in remote sensing to try and use habitat descriptors. It dates back to the very beginning, really, the original sort of Earth observation satellites. Now, it can be useful for wide generic classes, e.g. desert, mountain, sea, forest. And you're probably thinking to yourself, well, surely this must be okay. Surely a field surveyor can agree on that. Well, even here we run into issues when you're doing field survey. Where does the desert end and the mountains begin, for example, in this picture? And by the way, this is not the Pennine Peak District. And how many trees in one place before it becomes a forest or a woodland? And is that urban? And if so, where's the boundary? Now, the questions here are, will every surveyor make the same choice on the same day about where these boundaries exist? To be honest, even if we were to use this kind of classification, it doesn't contain a huge wealth of information. I mean, if the Peak District changed from ocean to desert, yeah, you've found a change you can map. But MFFP, we're kind of looking for more detail, I think. So why not simply subdivide these generic classes? Well, if you try that, things actually really go wrong. Now, here's an example of a typology used in the past few years in the Pennines. This is Kinder Scout. Now, it looks pretty enough, but this is the typology they used. I mean, simply look at how many heather classes we have here. Now, you're going to tell me anyone can tell heather moderate from heather moderate heath mosaic, or heather dense consistently, and heather cotton grass from heather cotton grass mosaic? I mean, I've written WTF here in my notes. There's no way these classes can be unambiguously identified in the field every time by every surveyor. Now, as for cotton grass wet and cotton grass dry, well, yeah, the stuff I've walked on in the past, it kind of depends on the previous month's rainfall, to be honest. Now, that is a section of a large-scale map, and here it is zoomed out somewhat. And it's a very pretty picture indeed, I admit. It's lovely. Although I chose the colours, so I'm kind of biased. Now, I'm not going to tell you who did this, or who produced it, just that it wasn't us. This map was one of those supplied just as a picture with a key. There was no accuracy statement of any kind. Nada. Now, when it was independently checked, it had an average accuracy of less than 10%. Think about that. Less than 10% accurate, i.e. 90% wrong. Now, actually, the kappa thing here, most of you probably wouldn't have heard of that, but Coa's kappa is simply a measure of how the classification compares to randomly assigning the classes to pixels. The scale runs from -1 to 1, and 0 is no better than random. Now, trust me, 0.08 is, well, this is a recording in a public forum, so I'm not going to say, but it's not good, should we just say that. Now, interestingly, the top three classes, i.e. those that have pulled the average accuracy up to the dizzy heights of 10%, none have got any relevance or pertinence to upland monitoring or MFFP activities. Well, unless they've taken up gardening on the side. Now, actually, this is one of those very clever sounding data fusion approaches. And I suspect the high conifer, garden and grassland values actually come from other data sets, i.e. Ordnance Survey boundaries, forestry and agricultural registers. Now, on the other side, the ones that are really quite important from the point of view of conservation and MFFP activities. Now, it's remarkable because the staggeringly low value for Kaluna and Bare Peat is just weird. We've always found these easy to map, or relatively easy to map, at all scales. Now, I think most of this results from that totally inappropriate typology. Okay. Right, now the elephant in the room. And apologies to Banksy for nicking this. Please don't sue me again. I'm sure many of the ecological surveyors and land managers amongst you are thinking, well, why not use the NVC? After all, this is the gold standard of vegetation survey. If you'd done that, surely nobody would complain. It would be completely uncontroversial. Well, I suppose that's true, but it would have been utterly useless. The NVC was not designed for monitoring. And I repeat that because these are the words of John Rodwell. The NVC was not designed for monitoring. I mean, feel free to use it how you like, that's up to you, but it was simply not designed for this role. Now, I suspect that's probably annoyed some of you because it's been going on for years. So why is this? Well, let's just consider how it meets our need for repeatability, i.e. to get the same result on the same day. Now, in 2008, a team led by Hearn executed a project, and I'm going to say this wrongly, guys, and I apologise to the Welsh folk in the audience if there are any, a project at the Hafid estate, an area essentially comparable to MFP domain. It was wet heath, dry heath, bog, acid grassland, bracken, millennia, etc. Pretty much analogous to the Peak District. There were 7 surveyors, all of them professionals, and they all surveyed the site within a short period. There was 1 statutory agency employee and 6 consultants, and they all provided with the same information, which in this case was a 1 in 10,000 ordnance survey map and a 1 in 5,000 aerial photographs. Actually, you should note that these are extras to improve mapping and not formally part of the NVC process. So how well did all that turn out? Well, here are the maps they produced. Now, I know you're thinking it's a real pity that they didn't actually use the same colour scheme, because then we could have compared them all. Well, they did, of course, I'm just teasing. And here is the key to those particular maps. Here's the legend, or the key, if you like. Right, how good did they agree with each other? Now, at the coarsest habitat level, these are really the chapters in the NVC books. They agreed at roughly 78%, say, at the habitat level. Now, I'm saying that is bog, that's woodland, that's grassland, that's sand dune. These are the really, really coarse habitats. It's highly surprising they agreed. Now, at the true NVC, the community level, things like M25, etc., it was only 34% agreement. 34% agreement. And when you come down to the sub-community, which is the things that you would want to be considering using for monitoring if you were to do this, the agreement between the maps was only 18%. So you could say that basically the whole thing was 18% accurate from that point of view. And I put yourself in the mind of a land manager. You employed surveyor A 1 year, and then you got G at the end of your project. And these are the maps they gave you. I mean, could you tell diddly squat from this? I don't think you could. Now, this paper should be mandatory reading for all land managers, conservation ecologists, and the like, especially, and also those who pay for such monitoring or site assessment work. There's a lot more in there than I've covered, so it's certainly definitely worth a read. I would just say that using NVC for monitoring is not science in any way, shape or form, and we simply didn't think it would be used for us when we moved on. And of course, there's something as rigorous as NVC, and I put the words in inverted commas here. What about informal classifications like, as we said earlier, dense Kaluna, medium dense Kaluna, less dense Kaluna, Kaluna areophrum mix? This is worse still, but even less useful. Now, why are we labelling this point? Because surely this is remote sensing. What's it got to do with field survey? Well, okay, it's central to everything you do in this type of remote sensing. And if you cannot agree in the field what something is, then frankly the computer has no hope. And apologies to those of you too young to remember this particular reference. We'll do a quick degree, as I mentioned earlier, remote sensing in a moment. But in essence, you have to tell the computer what to look for. And that's somewhat simplified, but that is the essence of how you do it. And if two people cannot agree on what they're looking at in the field, you simply don't know what to tell the poor thing. No, actually it won't say no. It will just go away quite quietly, unless the fans are wearing too much, and make you a very pretty but utterly useless picture. You can stick it on your wall, on our website, absolutely wonderful, but it won't tell you anything to help you with your monitoring. So if attempts to define habitats or communities with accuracy are essentially rubbish, what did we do? Now, I for one, especially as I am one, I'm not suggesting that field ecologists are incompetent people in any way, shape or form, because actually they can all agree on something. One thing in particular, and it's very simple: species. I mean, we've got books and everything to help us. Indeed, this is the first step of NVC anyway, so why not just stop there? Now, species are very seldom used as a typology in remote sensing. This is because there are actually few plant species that are resolvable to the typical Earth observation imagery of the past, which was about tens of meters. Now, obviously these days, with improvements in technology and whatever, satellite resolutions are getting down to around about a meter. Previously we had 25 centimetre of manned aerial vehicle imagery, whether it was film-based or digital. But all of these are only really useful for very few species. Trees, obviously, and not much else. But we were seeking to use pixels of less than 5 centimetres. And at that scale, species are resolvable. Now, many of you will already know this, and basically I'll go over it again just to make sure we're all in the same place. Firstly, all raster images are made up of pixels. I know you know this because you've seen them on Crime Watch or similar. Police seek retired ecologists for being patronising in public, that sort of thing. Now, these are the smallest unique unit of any raster image, the same colour, the limit to the resolution, if you like. Now hold that idea. Now, how do we do field survey? Right, well, step one is to pop out into the field for a little bit and do some surveying. I mean, take a picnic, take a flask. Actually, for this project, the field work comprised many weeks of work. And again, well done to you and team. What do you do next? Okay, well, in the morning when you get back from the pub, and I'm simplifying a lot here, but what you simply do is to show the software a series of pixels of the classes you identified in the field. Okay, so you've mapped where your pixels are on the ground, and you match those to the pixels in your image. This is usually called training, i.e. you're training the computer to recognize your classes. We'll come on to those in a minute. Now, this means you have to know exactly which pixel in the picture is the one you identified in the field. Now, as we use pixels only a few centimeters, this was not a trivial issue. And as you can see here from the zoomed in, very much zoomed in pixelated picture, the one I've picked here happens to be at the intercept of 4 pixels. Well, these things happen. Now, I'll explain how that was covered when talking briefly about the field work in a minute. But during the training, or the computer training, we tell it to integrate or average the pixels within a 10 centimetre region. So it will basically pick these 4 as well. Now, I said we didn't use any academic black arts, no jiggery pokery. That's true. There isn't any here. What there is precision. DGNSS or DGPS for field work. This isn't rockety science, for heaven's sake. No, I suppose actually in a way it is a bit, but never mind. And I think these days this needs to be considered minimum equipment. I'm an ecologist and I remain totally embarrassed that, barring a little bit of excitement with colour pencils in the 1990s when it came to phase 1 survey, the newest tool on the majority of my colleagues is Neolithic. And here's a nice cartoon. Here we can see the first plant surveyor. He's getting his first quadrat. Now, we seldom seem to have moved on from this, and it's frankly ridiculous. But there again, I go moaning again, so there, I'll move on. Okay, what happened then? Well, phase 1 was the first test of the plans, protocols, image acquisition, you name it, to map those 11 square kilometres. And yes, we all know about Rabbi Burns' best laid schemes of mice and men. Fieldwork, how did we do it? Or what was it about? Well, firstly the surveyors were told to identify 50 by 50 centimetre minimum area pure stands or swards for each species they found, and record the centre point using the DGPS. Now this minimum size was to allow for some leeway, if you like, between the ortho-correction of the imagery. Remember the registration between the fieldwork and the centimetre scale pixels? We were never going to be able to match exact pixels to exact 5 centimetres on the ground. There's too much local variation in topology for that. So we wanted a little bit of buffer around, if you like, and the 50 by 50 centimetre fieldwork limit was designed to do that. We also asked them to seek a minimum of 100 samples of each species, roughly in line with the recommendations from likes of Calder and etc. Now the sites were imaged using Parrot Sequoia and RGB at around 70 metres in 2018. And this was not the original sensor platform combination that we planned for. So a lesson here, and I did say it was lessons and limits, the big lesson here is how easy it is for these things to break and the immediate impact it will have on your planned monitoring program. Now the only short-term alternative available was slightly different than the one we had planned to use, but never mind. We took the imagery and it was auto-corrected to around 2 to 4 centimetres, less than the pixels, so we were happy, or less than the pixel size, we were happy with that. Okay, so what happened next? Well, here's a bit more dirty washing. These are more lessons. The expectations of time staff required for field work was underestimated. Not by little, by a lot. It's very hard to predict how long somebody's going to take to do something, it really is. The use of the DGPS logger, finding the appropriate size stands, transport backwards and forwards and walking to the site and over it, all contributed. So sample number actually gathered fell well below what was needed. And that caused a problem. We decided at that point that what we were going to do is to use all of the data, all of the field data for training image classification. So no accuracy assessment was possible except at one site called Fermin. Let me just explain that a little bit. When you do your field data, you split it randomly 50-50 and use half to train your computer and process the imagery, then use the other half to test how well you mapped your result. And that we couldn't do, apart from one site called Fermin, we just probably had enough because of the shortage of field data. But it happens, it's lessons, you don't know these things until you try them. Okay, these are simply some pretty pictures from Fermin. Now, I did say we aren't going to do just pretty pictures, but before we do, look at the accuracy results obtained. Just note, of course, this shows you the abundance of all the species on the site, and also, of course, the location of where they're occurring. So what was the error matrix? Or these are called, by the way, these are called confusion matrices, and that's just because they're pretty confusing. The overall accuracy was only 43%. That's not earth-shattering at all. But it was a first attempt, which is one of the reasons for this. But I think the main reason is the very low numbers of samples. As you can see, for most species, they're well below 10% of those we decide. So, which is why we couldn't ever check the other sites. But it's not all totally cup. I mean, one of the expected things, Bear Peat, one of the specific mapping objectives of this project, has already been mapped well. And the other Aclophus group, Bear Rock, well, yeah, I'll go with 100% accuracy every time. Don't get me wrong. Despite the rest of this is already still worth doing. Not least, don't forget, it was the first attempt to map species using UAVs in this environment. And then something else popped out of it. Really something quite important, and taught us something really very important. Let's go back to that picture again of Fermin. Can you see something here you might not expect? Well, this shows the flight direction of the UAV. Now it has to make repeated passes to cover the area, up and down, rinse, repeat. Now if your screen and my internet allows you, you should be able to see this banding or striping in both the RGB imagery and the NIR imagery in this matching a line of flight. And it's especially clear in the classified output. Other sites look the same. This one is rolly, although the flight line is in direction. The effects you can see are the same. So why is this occurring? Because it's certainly there, and as we say in a technical term in remote sensing circles, it's buggering up the classification at their end. Right, let me explain why it is. But firstly, I'm going to explain to you that I'm going to lie to you a little bit here. It's for your own good. I'm not doing it deliberately, or I am doing it deliberately, but it's for your own good. It's to simplify things, just trust me. So the coming diagrams are wrong in nearly every possible way. There is no image capture system that works in the way I'm going to tell you. It never really has, but it illustrates the point perfectly. Now, satellite EO, Earth observation, with resolutions of a metre or so, will collect something like this essentially in one go. You could call it a footprint if you like, although the swath is the correct term for the width of the coverage in the line of flight, if you really wanted to know that. Now, MAV. An MAV, a manned aerial vehicle, will cover this sort of area in one go. And again, all the caveats about lying to you and whatever else and simplifying it is appropriate here as well. But this is the sort of area you can imagine we're getting in a single image. Now, let's consider our UAV. There it goes. Up and down it goes. Now, the footprints it takes are tiny. Now, this will continue for quite a while in the background, just like real life really, except it's speeded up an awful lot here. Probably take an hour or so in real life. UAVs carry cheap and tiny sensors. They get a very high effective resolution or ground sampling distance by flying very low, typically 100 meters or so. Indeed, they're restricted by altitude by law. So they have to take hundreds and hundreds of images to cover any reasonable area. And this takes time, a long time. For the area we did, it was typically an hour or so per flight. And the area you can do in one go is also restricted by CAA rules. You cannot fly beyond 500 meters line of sight from the operator of the UAV. So you may also have to relocate the operation as you proceed. Also, if you're doing two sides of a hill and can't see across it, of course. And then, of course, you've got battery changes because they don't fly all day on one battery. So it takes a lot of time compared to either the manned aerial vehicle or Earth observation. If anybody wants to know how that was simplified for clarity, or how I lied to you, please ask at the end. The truth is a lot worse than I've made it seem. I've just clarified the essence of it. Okay, now why should this matter? Well, and this is a typical Morse future field lunch here, as you can see. While you sit in the sun having a champagne, canapé, etc., watching your UAV fly around its pre-programmed course, this being the UK, clouds and patches of open sky, etc., come and go. It'd be very unusual for it not to, really. So while this is happening, not only is the intensity of light, but the colour temperature is changing within these patterns. And of course, not only that, but the sun angle shifts by around 15 degrees an hour, meaning the shadows are shifting as well. Now, I know you're thinking this probably, but surely these things are clever. They've got automatic exposure and stuff, just like my phone. Well, ideally, in this case, it's called a Day-Welling sensor. Of course, they should have. It's kind of analogous for an instant light reading for any photographers out there. Now, yes, of course they can do that, but as any photographer will tell you, a picture, for all of you know this, any picture taken in full sunshine does not look the same as one taken under cloud, in a cloudy day or a dull day. The average exposure might be balanced, but they look very different pictures. Now, with the UAV, when you mosaic all these images, you get something like this. I've exaggerated it here, obviously, but this means that to the computer, you're giving different coloured samples, different pixels, that you're telling it are the same species, but the variation in colour is depending on where the samples were in the image and hence the time they were actually imaged. Now, maybe you're thinking about ways of working around this, classifying strips or some images separately. And generally that just fails because if you've got very low sample numbers or none at all in some parts of the image. And if you try to mosaic individual classified products, well, anybody who's tried that will tell you they don't match at the edges. Never happens. Okay, we're learning things. Let's just look at phase 2, or I know what you did next summer. How did we respond? Well, number 1 was fieldwork. We incorporated 2 major changes here. Firstly, we designed a streamlined, a bespoke and streamlined, much more efficient data entry interface for the Trimble logger. Previously, surveyors simply used a Trimble default. This was basically simple for us to do, and in effect proved much quicker in use. Perhaps more importantly, we created a formal survey structure. During phase 1, surveyors had just kind of wandered around aimlessly. Well, that may be a tad unfair, but they had no formal guidance. And this led to very poor coverage across the actual sites. Now, this time we used a variation of what's usually called cluster sampling. Surveyors were given the lat-long coordinates of 100 loci per square kilometre as a 10 by 10 grid, as you can roughly see here. Now, these were walked to in sequence by the surveying team using a simple GPS go-to function to start at 1.1 and move on to point 2. Now, at each of these loci, the surveyors search within an approximate 30-metre radius for samples of single species stands meeting that minimum 50 by 50 centimetre criteria. As they found them, each was marked with a flag, and the surveyor carried on looking. The recorder with the data logger then moved from flag to flag, logging location and species. Now, the reason for this was that logging takes quite a few minutes, to get enough carrier signal and also to enter the data and double check it and enter the point. So by doing this, we freed up a lot more survey time, because previously they'd all worked as a team, and while one person was doing one thing, the rest of them were just waiting around. A bit like cancelled roadmen leaning on shovels. Well, I shouldn't be. I'm not being cruel to you, you know that. Now, using this structure forced a comprehensive coverage of each square kilometre, but it doesn't impose specific sample locations. We couldn't do that because the constraint of the 50 by 50 area would mean that if we gave them thousands of coordinates at random within a GIS, most of them would have been inappropriate for use because they'd be too small. So it would have been woefully inefficient. So the approach adopted was efficient, but it was not unbiased. So you need to remember that you cannot do statistics on these field data. It's a pity, really, without a doubt. But all the other methods would have been far too laborious. I think in future, if there was opportunity to find a bit more time, I try and do both, a mixture of these. But this depends on staff time, clearly, and it remains the one thing, but it still remains the one thing I wish I'd really done. Here's an example, quick example picture of distribution of points or currents, wherever they are, over 1 square kilometre. In total, there were 7,000 field records. That's an average roughly of 1,300 per square kilometre. Each site took between 13 and 16 days. But we still did not achieve a minimums of 100 per species. Now, we'll come back to that in a moment. And I've put here bias. That's just what as I've just said, it means it's not open to normal statistical analyses. But we got a lot of very good data, and we got very good coverage. We completely solved the problems that we experienced in phase 1. So how about imagery? Well, when it arrived, and I do say when advisedly, it was very good. Ultracam, flown at 2,100 metres above ground level, gave a 10 centimetre resolution, roughly the same as the UAV we were flying. Author correction was within acceptable limits, considering this minimum field unit that we're talking about. And all sites were covered in about 20 minutes. I mean, realistically, it was far better on UEV on all counts for the areas we surveyed. Yeah, but. There's always a but. Are you getting used to this yet? This is what I meant by limits and lessons and limits at the start. As you can see from this view of Kinder, I'm focusing on Kinder because it's quite pretty for most of these pictures, but you know, it applies everywhere. Yeah, it wasn't flown until October. The reason being a contractor experienced delays because of Manchester air traffic control for one of the sites. Now, had the communications between the supplier's operations team, their sales team, Moors to Future Partnership, and us all been rather more savvy, some of this might have been mitigated. We could possibly have asked them to exclude one site or to fly lower. These are all good 2020 hindsight. Like I say, lessons. You learn from these things, you find out, and sometimes only by making slight, not mistakes really, just not picking an optimal route forward. So in this particular year then, you can see that the low sun angle created tremendous issues with shadows, because it's October. Not just the large areas you can see here, but alongside every rock, every plant, etc. Then of course you've got phenology. An awful lot of the plants now in September have senesced, they're past their best, they've moved on, they've hunkered down for the beginning of the winter. So that's not going to help us either. So ignoring all of that, because hey, we had to, or we wanted to learn more. It was a full survey and we had some imagery to match. So our first chance really to look at the spectra of the vegetation and the sites and examine techniques and classification approaches and such like. And firstly, we just eyeballed the data using simple ordination analyses. This is the first two axes of a CCA of species in spectral space. We just use it to visualize the potential of species classes to differentiate from each other. There are other approaches and we adopted those too. But this is a good visual method. The clustering here, as always, is interesting. In case you're unfamiliar with it, what it simply is that the things that are farther apart, the greater chance they are that they will separate out in classification, i.e. they differ enough in spectral space or four-dimensional spectral space. Okay, and of course vice versa. If they're close together, they are so close in spectral space that frankly you haven't got much chance. There's always things to pick out of this sort of stuff. As you can see, chlorophyllous, i.e. green stuff, and achlorophyllous, non-green stuff, plants and non-plants, sit nicely on a vector driven mainly by NIR, near infrared. This is, what should happen. But it does show the kind of the visual things you can get from this. Now look at this Sphagnum, I mean that's particularly interesting, and there's a lot to discuss here about potentialities for why this is occurring, why some are clustering, and why some are separating. It's interesting. Other stuff, say look at the Coluna flower and descamps here in the upper right quadrant. Well, I mean that's not going to go very well, is it? Yeah. So we also decided to try classifying because hey, that's what we were here for. Now we had shadow, don't forget that, a lot of it, more than you'd like to have. Now there's no good way of dealing with shadow in remote sensing, especially as bad as we had it. Now in the document we discussed the merits of the differing ways of approaching shadow in your imagery. Now for this particular report, in the end we decided the best way for us, in this case let's say, was to treat it as a discrete class. I'm not a fan of this, don't get me wrong, but there was reasons for doing it here. And we train it as shadow, and we classify on that, and we test for errors. So we visually examined, and I use we here, sorry, very loosely. Should I say Ben visually examined all samples, all 7,000 of them, in the imagery, and those affected by shadow were recorded as, we recoded as shadow. Okay, you might think you should pre-classify using this shadow to separate it out and then just block it. It doesn't really work because it can look so similar to things like wet, bare, peat, for example. You just need to do it by eye, sadly. So our first process here was firstly to clean up the data. That was just to remove the samples that the field notes declared as not reaching the minimum aerial extent of 50 by 50. You wonder why they're in there, because the surveyors were told not to record anything smaller than 50 by 50. But in reality, when they got to the field, there were things of interest that they wanted to note down and record, which were obviously not useful to us, but they were still useful information that they're gathering for the purposes. So we had to trim those out. Now once we'd done that, we had 4 iterative reductions or subsets of the data that we extracted by removing species, progressively removing species with less than the desired minimum 100 samples, the least first. So basically we did 4 cycles of this. We call them A, B, C, D because we're really original in naming our data sets. So these were progressive reductions in the sets by leaving out species that, say, only had 3 or 4 records originally, and then we'd work our way up maybe to those that only had 10, and we'd progress that way. So we had 4 discrete sets of data that we then trained and classified and compared the results. Now, it's a huge amount of work here. There really is. It's all in the report if you want to plow through it. I'm not going to go through it now because everybody would fall asleep, and so would I, and we'd all wake up on YouTube 8 hours later snoring. Well, yeah, let's just move on. Let's look at the accuracy we achieved in this case. Well, the observant and the still awake amongst you will say, hang on, that's almost the same as the rubbishy, stripy UAV stuff you said, and you've got loads more samples and you've got better imagery, haven't you? Well, yeah, it's not that good, is it? And I said it's October, half the stuff is dead. And the impact of shadow is very clear here. For example, bare peat, normally a very good classifier, actually is a low user accuracy, and that's mainly because of the confusion with shadow, which is why we've classified on it, trained it, classified on it, and put it into here so we can see what it's causing the main confusion with. Clearly is not too bad at all. This is, by the way, is 3 cleaner classes pooled, normal, Sonest and burn, classified separately because the signatures are differently, and then we merge them into a common class and error check them. Look at Angustifolium. Well, there you go. It classified remarkably well, and I'm going to take 90% every time, thank you very much. And of course, those of you who are familiar with this environment will know pretty much why that is straight away. Yeah, you take a picture in autumn, winter, and it's pretty much the only orange thing on the hill. Now, this clearly demonstrates a couple of lessons here to be pondered. Firstly, it's the issue of plants pretty much being all green, and I'm happy to discuss that ad nauseum in questions at the end if you wish. But plants essentially are mostly green. So all the differentiation pretty much has to occur on one spectral axis. When you get something which sticks its head above the parapet, if you like, and decides to just appear somewhere on a different spectral dimension, hey, it gets picked off really easy and classifies out well. Now, this identifies something that's very important. It's called multi-temporal imagery, and using that for classification. Now, some species change through the season at different time, and some species change less at different time. So, all being green doesn't really apply because one species is green at a particular period, another species green at a particular period, then one species is flowering while a different one isn't. So, if you acquire 5 or 6 slices or time slices of imagery, then you can pool these and use these differences as well within your classification algorithm. So that's a useful thing, but as I say, not available right now. So you're thinking to yourself, well, maybe despite what you said at the start, we should stick to pretty pictures. After all, we were getting used to it, and we had quite a lot laying around, well, actually pinned to the wall at the moment. So where were we? Well, in summary, And there simply is no way to avoid the fact we were 2 years into a 3-year project and we didn't have a lot to show for it. Everything kept going wrong. But phase 1 had taught us and MFFP a lot, mainly the time required to fly and survey large images and the poor imagery you get owing to striping because of changes in illumination. Also taught us about field work and how difficult it is to estimate the time required. And phase 2 had taught us an awful lot too. How to obtain great field work, and then maybe how to go back and look at the contracts for when you specified that imagery should be acquired. So we began to re-examine the constraints you put upon the imagery company. And yay! We had a third go. The air was flown in June 2020. This time, owing to both a lower altitude and a brand new sensor, the ground sampling distance was 5 centimetres. That's vastly higher than expected originally, or achieved with the UAV. There's a few additional ortho tweaks, that's what I'm saying, talking between, working with the supplier. We had to provide extra ground truth data and backwards and forwards, and we get remarkable results. We got very, very good ortho correction in the end. Okay, this is a small patch of Kinder, about 4,000 square kilometres. Again, I like Kinder, don't know why. This is 2019 imagery. This is what we got from phase 2. So you can see here the shadow. Okay, fine, that's all right. Now, I've been working in this sort of thing for a long time, and when you're used to satellite imagery and the rather more usual 25 centimetre, the old-fashioned film-based imagery, this is pretty good stuff. I mean, look at the scale bar, the 1 metre scale bar down there. As I say, to be honest, until around a decade ago, this was the sort of stuff that we were looking at, and this is actually 25 centimetre resolution imagery, and this was standard stuff until less than a decade ago. And we were used to working with this over many, many partners for very many years. Let's just go back to 2019. This is what we got in 2019, and we were pretty impressed despite the fact it was, should we say, shadowy. So what happened in 2020? Well, this was 2020. Now, like I say, maybe I'm looking at imagery for far too long, but this almost makes you want to cry. Yeah, okay, maybe it's a personal thing. This is what 5 centimetre manned aircraft ultracam imagery looks like. And it's consistent over large areas, unlike a UAV ever will be. It's not only the resolution here, of course, that jumps. You can see that it's fourfold in area terms, but of course the changes in shadow. You can. This is taken at the right time of year. This is taken in July. So I'm just going to do that again because I do like that. This is 2019, and you can see the shadow, but you can see the resolution. Remarkable, isn't it? This is just, yeah, superb. Well, look, here it is classified. Now, there's a lot to look at here. It's a pretty picture-ish. But we also know the accuracy. Before we move on, I just want to point out some of the bad bits. I said I would, and this is an honest presentation. We're not going to hide anything from anybody, okay? It just flatters you to deceive others. It's pointless. One of the things I would point out here, because it's probably funny next to yourself, is the areas mapped as dead Kaluna. Now, this was a class that shouldn't really be in here, I don't think, because I think if you're picking a 50 by 50 centimetre minimum field unit, you don't see solid dead Kaluna as a sheet. What you see is some bits of dead Kaluna. So when you're looking down from above, vertically above, you see sticks, but you see what's under them as well. You see through to the ground. Now, we don't know what that was. Now, these samples were included in the field data. We weren't going to exclude them. As I said at the start, we're playing on this brokers here. If we start deleting what we don't like, oh yeah, we can force the apparent accuracies up. But you wouldn't then, in this particular case, map the dead heather where there was some. So it would appear right wherever you mapped it, but it would be inflating the accuracy figures wrongly. Now, I'm not going to go right now into the true meaning of accuracy tables and how they can lead you a merry dance if you don't treat them cautiously. Again, if anybody wants to know, there'll be questions afterwards. So my feeling is that we had a slight problem here because there'd be some bare ground under here, there'd be some actual dead Kaluna, and there'll be pixels of understory, bryophytes, maybe even young heather growth. No way of knowing because it's all been aggregated into this one dead heather. So let's not do much about it. One point I will point out here, well, why not? Some remote sensors here might ask, why not use a priori probabilities? Well, we can't because our data are not unbiased. The recorded frequencies are not the actual occurrence frequencies. So that's really not that valid. But I think we're getting a bit esoteric here, so let's move on and look at the accuracies. Okay, now an average of 57% for all sites. It's not earth-shattering, to be fair. Okay, but we are mapping species. We're not mapping, I don't know, bog, rock, mountain, desert. We're mapping species, plant species, for heaven's sake. It's not too bad. But of course it's an average. Now if we sort these into two groups really quickly, these are the two classes in these two groups, the good, the bad and the ugly, or maybe just the bad and the ugly, or something similar. Those on the left are pretty good. They're within an acceptable range, and I would kind of think these are going to prove to be useful to you to monitor. Note that they are primarily the big players here, the ones that have most importance for monitoring MFFP requirements. And they're probably the same as yours if you're following this talk. The dwarf scrub heaths, Cluder and Vaccinian, bare surfaces, peat and mineral, both the aerophrons. Okay. Now on the other side you can see the poorer ones. Now I've put Youngcus, effusus and Nardus in both categories here because they're on the cusp, I think. So what do we think? The results here, and it's something I've been sort of suggesting to students for many, many years, is that remote sensor accuracies haven't varied much over the years. They're always typically about 80% because they're doing broad categories and that's the limit of the system, the whatever. But here we're doing species, and we're getting 60%. So yeah, I don't know. The key thing here is that there are no field data ambiguity. If you're using an ambiguous class like dense heath, dense heather, then first of all there's mush and muddle in your field classification, and then there's also the mush and muddle of how well the algorithms classified it. So I don't think you're going to get better imagery than this for a long, long time. Yeah, I know people always say these things, but these cameras, we're talking in millions of pounds. The investment cycle is not that fast. I don't see us getting much better than 5 centimetre 4-band imagery of this quality, improving upon that any time soon. So we could have more field data. Everybody wants more field data. We would have liked classes with, certainly more. Those ones we hadn't got without 100, we certainly would have backfilled those. But this accuracy figure, well, what's it mean for monitoring? Well, it tells me, frankly, it would be pretty perfect for a broad brush, large area survey, for knowing what is where, flagging areas of interest for intervention and such like. You've got a map, and you know where the species that you've mapped are, and you know where to go looking to do the work. Now I'm going to hold on here, with a pretty picture of course, because it's time for me to shut up.
And I'm going to take you through the next steps of the project. Thanks, Adrian. So, Phase 4. Now, at the IUCN conference in September 2021, we reported 46% accuracy mapping species. Phase 2. Today, September 2022, Adrian's noted that we reached a dizzying 57%. Phase 3, which is an improvement of around 10% per year. So Phase 4 should deliver about 70% accuracy. And then why not add another 3 years and we should be nearing 100% accuracy. For mapping species, unfortunately not. With what we believe is the best achievable 4-band imagery in terms of the combination of spatial resolution and spectral fidelity, around 60% accuracy seems to be the limit for mapping bog species, or at least some bog species. It's important to remember that this was only species with high sample number. Species with low sample number were excluded, and these species will inevitably have mapped to something else, albeit incorrectly. But, as Adrian has pointed out, some species classes map with high to very high levels of accuracy. So there is clear application for species mapping. But it did not seem to be a good use of resources to focus further time on mapping individual species. So what did we do in the last year? Well, firstly, we explored aggregating or grouping species. We know that the spectral characteristics of some species in 4-band imagery are not sufficiently distinct from that of other species. They overlap in spectral space and are confused in the classification. Some of this confusion includes species that are not necessarily of immediate value for conservation. But grouping species might be expected to result in higher overall accuracies while still retaining relevance for monitoring. So we tried 2 approaches. For the first method, Moors of the Future provided us with 2 sets of simple taxonomic groups determined to be relevant for monitoring. We had a smaller set of 7 key groups or classes and a slightly expanded set of 12 classes. You will note that bare peat, ferns, mineral soil and rock are present in both. Now some of these groups may appear similar to plant functional types that are referred to in other studies. And it's worth noting that this approach does not take account of the spectral characteristics of each species. So it might not be expected to produce a substantial increase in accuracy over species mapping. The second method aimed to identify similarities in spectral characteristics and create groups with minimal spectral overlap. In contrast to the first method, this approach might be expected to increase classification accuracies, but it might create groups that have potentially less value for conservation. For example, a group might contain plants and bryophytes that have similar spectral characteristics. Now, some of you may be thinking that Adrian spent several minutes telling us not to map communities or habitats. And you're right, and we didn't. We used the species field data, and we grouped those samples. So there's no ambiguity as to what is in each group. An advantage of grouping was that we were able to add species with low sample number back in. It doesn't matter now if we only have 3 Agrostis samples, if they form part of a group with more than 100 samples of other species. And while we were exploring grouping, it also seemed relevant to explore alternate classification approaches. We needed to check that the classification approach adopted at the start of the project was still applicable, and we know that more modern machine learning algorithms such as random forest classification are seeing application in peatland studies. The third member of the team, Dr. Thacker, our mathematician and statistician, spent several weeks running through a number of spectral similarity analyses, and Adrian and myself eagerly awaited the results. And when they arrived, we discovered that class separability and unsupervised classification did not provide an improvement in accuracy. In the third iteration of analysis in spectral space, which is similar to the ordination Adrian showed you earlier, we saw a small improvement, almost 10% for the year. And then we tested the Moors of the Future groups. And you can imagine the expression on Dr. Thacker's face. The lowest performing Moors of the Future group produced an accuracy comparable to the best performing spectral aggregation. The smaller Moors of the Future group, of 7 classes, achieved 75% overall accuracy, which is a marked improvement over species by almost 20%. And that includes previously excluded species. Now this was surprising given the fact that this approach did not take account of the spectral characteristics of the species, but the groups have clear relevance for monitoring purposes on a range of levels. Of additional note, the random forest classification produced an accuracy slightly lower than maximum likelihood classification, demonstrating, at least for this purpose, that traditional classification approaches perform just as well or perhaps slightly better than modern classifiers. Now we examined species aggregations over a test area, and we had to know if our exploratory analysis holds at landscape scale. And it does. We achieve 73% overall accuracy over 11 square kilometres. Bare peat, dwarf shrubs, grass sedge rush and rock all map with 76 to 86% accuracy. And these are all higher than the overall accuracy figure. Bryophytes map with an acceptable accuracy, 63%, still higher than species accuracy overall. And yes, there are some lower performing groups. Ferns and mineral soil map at around 40%. So are these suitable for monitoring? At the start of a project, you may need baseline data. If your site is dominated by ferns and mineral soil, particularly the latter, it seems unlikely that there's any peat left. But with 76 to 86% accuracy, you can determine if your site is dominated by bare peat, dwarf shrubs, or grass sedge rush. Over time, you might want to know if the area of bare peat has reduced. You can map this with a known level of accuracy, 88% here. The expanded, more detailed groups did map with a notably lower accuracy, 60% overall. There are more classes. But again, there are classes of value. Perhaps you are specifically interested in changing heather rather than all dwarf shrubs. Here the classification accuracy achieved is 81%. And you don't have to stick with one classification. It might be useful to combine information from both species groupings. Sphagnum is mapping with almost 60% user accuracy. Okay, it would be good if that was 79% or 84%. But as long as you know the accuracy, you can map sphagnum. Now, so far, we've shown you pictures. And we've reported how accurate these pictures are. But is this what you really need? Probably not. You want data. You want an estimate of the areas of land cover in your image or site. The area estimates come from the classified product, and the error matrices have additional use as they provide crucial information on uncertainty. Now, it's also worth noting here that classes that map with low accuracy typically have low presence. So don't just rely on the information in error matrices. Now, of course, this provides the same information that ecologists derive from quadrat surveys, including their uncertainties. But remote sensing provides data over far larger areas, and it allows you to capture that in a much shorter space of time. So phase 4 demonstrated further capability of remote sensing for monitoring. Species aggregation using the smaller set of more future groups provides a marked increase in accuracy over species mapping, typically 75%. Key groups, bare peat, dwarf shrubs, grass, sedge and rush are all mapping with 76 to 86% accuracy. I mentioned you may want to use more than one typology to get different information. You could even go back and include species mapping, because even at that point, Kaluna was achieving 85% accuracy. The data will allow you to extract area estimates. And most importantly, you have estimates of uncertainty to go with your areas. Now, this may only be suitable for 1, maybe 2 rounds of monitoring, as the error is multiplicative. If you have 89% accuracy for year 1 mapping, when you use change or determine change in year 2, that's going to be reduced to 79% or lower if you don't achieve 89% in year 1. But the key thing behind everything here is all approaches rely on mapping species in the field. Okay, so as Adrian highlighted earlier, the project planned on using UAV-derived imagery. But we were not able to test it fully, largely due to low sample number, but we did have an indication from one site that accuracy was around 40%. In phases 2 to 4, we focused on MAV imagery, and we developed best approaches to mapping with these data. Now, as such, we have little evidence of the suitability of other image sources for conservation mapping. So we undertook a comprehensive test and compared the performance of UAV, MAV and EO satellite data to map the best aggregate classes. We focused on an area on Kinder, partly as this was the largest site containing the greatest number of field data. This area covers two more to the future experimental field labs, Fermin and Olaf Nogsen. The top left image shows the UAV data. These cover 129 hectares and does demonstrate that you can capture relatively large areas with a UAV. It's worth noting though that this took 2 days to capture it and involved numerous flights on each day. So with this sensor, the multispectral data in 9 centimeter resolution, and there are 4 bands: green, red, red edge and near infrared. Top right are the MAV data you've already seen, 5 centimeter resolution, blue, green, red and near infrared. Bottom left are the raw or native resolution data from the WorldView 2 satellite. I play satellite top trumps with my students, and in the cards the WorldView satellites are right up there, particularly for spatial and spectral resolution. There are 8 bands: coastal, blue, green, yellow, red, red edge and 2 near infrared bands, and the ground resolution is 1.5 meters. This is far higher than the 10 to 20 meter resolution data you get with Sentinel. WorldView 2 also has a panchromatic band, which enabled us to pan sharpen the native multispectral data and create a 38 centimeter resolution 8-band image. But we must stress that pan sharpening makes up pixel values. So although you gain spatial resolution, you lose spectral fidelity. And here are the classified outputs. And there are similarities between the maps, with a large area of bare peat, for example. But which area is best? And the only way to find out is with error assessment. Now, we did say that we weren't going to explore species classifications further after phase 3, but we had not tested UAV data fully or tested EO data at all. So we did perform a species classification. And the MAV data produced 57% accuracy, the same as that achieved in phase 3, which gives us confidence in the assessment and that the area we've tested is representative. The UAV data achieved 40%, which again is comparable to the 43% achieved in phase 1, but it's markedly lower than MAV accuracy. And the satellite data achieved more markedly lower accuracy, only 23–24%. The results from the species groups show a similar pattern. MAV data achieved slightly higher accuracies than reported in phase 4. We got 79% for the smaller group and 64% for group 2. But in all tests, species and groups, MAV data performed markedly better than UAV and satellite data. Now, the results for the satellite data were surprising given the increased spectral resolution. We had expected, or perhaps hoped, that the additional spectral information would help tease apart some of the confusion. But the field collection protocol was not designed for Earth observation data. It was designed for 10 centimeter resolution, 10 centimeter size pixels. Now, that doesn't mean that there is no application of Earth observation for mapping. There clearly is. But for WorldView 2 data, field samples would need to be a minimum of 2 meters by 2 meters. And it's unlikely that stands of individual species will exist in these dimensions. So to use this, you will need a different typology. And what was already been discussed is the problems in the field if you have to use communities or habitats. Species is the only unambiguous data you can collect. The previous data and analyses examined were all covering the main component, to monitor land cover change. As outlined, we learned a lot, and in reality, after 4 years, we're probably now ready to start a project monitoring land cover change. We've worked out the limitations and we can balance what is required with what is achievable. 2 further components were proposed: to monitor surface wetness and to monitor rates of peat accumulation and erosion. These were experimental and less time was spent on these aspects. But the back of our minds was the scope of the project, landscape scale, ultimately across the size of an area, size of the SAC. Now, in theory, standing water should be identified in land cover mapping as a class. But if water is not on the surface, what can we measure? Perhaps soil moisture? Water exhibits potentially useful thermal behaviour. It warms faster than land and cools slower. We may therefore see differential warming of soils in relation to the amount of water they contain. Now, we know that patterns in thermal infrared imagery from both MAV and UAV platforms have identified the location of drainage features and near surface flow routes. But no direct translation of thermal measurement into an index of surface wetness has been reported. So this is what we examined in this component. We were looking to see if there is a potential relationship between thermal imagery and peak surface wetness. We undertook this assessment at the Birch and Lee site. It's worth noting, this site, it's a 3 kilometre hike uphill with a lot of equipment, a UAV, ground control, DGNSS. Again, something to be thinking about when you're contemplating data capture. Now, we focused initially on a relatively small area, around 7 hectares, with a topographical or hydrological gradient, which we'll see in a minute. We captured thermal imagery at 2 times a day, and we collected 40 peat samples across the area between the flights, 10 centimetre deep cores that were 2 centimetres in diameter. So the red outline in the map shows the target flight footprint. Now, owing to the nature of the sensor, the area captured actually extends beyond this outline. So this sample was actually captured in the imagery, even though it's outside of the proposed or target footprint. We used ground control for image autocorrection, and we took samples in 4 groups near ground control targets to improve pixel and sample alignment. Samples were taken in areas of bare peat with a minimum dimension of 50 centimetres. And the erosion gully provides a hydrological gradient and a topographical gradient down slope. Now, we also took a number of samples in the gully, as it's reasonable to assume that water might collect in the gully bottom and the gully sides might also be drier. In the laboratory, we determined the percentage peak moisture by mass. It's a simple weigh, dry, reweigh routine. And for the analysis, we explored potential relationships between soil moisture and temperature. And these are the processed thermal imagery. The first flight was undertaken at 11:30 and the second at 14:45. We've clipped the data from both flights to the same extent for direct comparison. The minimum temperature was comparable, varying by only 0.4 degrees, but the maximum temperature increased by about 3 degrees. Now, it's difficult to visualise topography and the impact of aspect in 2 dimensions. But shown in 3D, it's clear to see that in the morning flight, southeasterly aspects were showing relatively higher temperatures, and in the afternoon flight, westerly aspects, particularly gully edges, were showing relatively higher temperatures in comparison to other areas across the image. So what did we find? Well, a significant inverse relationship between the percent peak moisture and the peak surface temperature was identified in both flight data. The goodness of fit is not particularly high though. We're looking at 17 to 26%. And the slopes are different. Now, some of you are probably looking at the point down here. Now, this is a real data set. There is always one point that doesn't fit. Now, we don't like excluding data, but we did collect data, a number of samples within the gully. So this is just to highlight the impact of the samples collected in the gully. The relationship is still significant, but the goodness of fit interestingly improves in the morning flight, but it reduced in the afternoon flight. But what does all this mean? Well, we've shown that it is possible to detect variation of water content in a bare peat surface using thermal imagery. But the slope of the relationship between soil moisture and surface temperature varied in just 3 hours. So this relationship will be affected by time of day, time of year, cloud cover, and other factors. So it's not possible to derive a single direct translation of temperature into an index of soil moisture. You will need to collect peat samples on every survey. And not only does that add time, you're always going to need consent to collect the peat. In addition, I thought that sounded a bit less negative than but, the relationship that we have measured or determined is for bare peat surfaces. And we're restoring our bogs, one of the aims being to cover bare peat. So if there's little or no bare peat left, you would need to use the temperature of the vegetation. Now we've seen that this varies markedly by aspect, and it will also vary by shading, phenology, and a range of other factors. So the temperature of a plant does not tell us about the soil moisture underneath. So at the moment, the application of thermal imagery for measuring surface wetness is not clear. The last experimental component was to monitor rates of peat accumulation and erosion. In essence, this is simply a change in elevation or topography between 2 time periods. And it's not necessarily new. Shortly after this project started, some studies, for example Glenville et al. 2017, have reported change within individual gullies from UAV-derived data. But we wanted to test what might form part of a landscape scale monitoring program. We had UAV data collected in 2018, phase 1, that provided baseline data in the form of a DEM, but we also had point cloud and mesh, 3D mesh. So we have a range of opportunities to assess change. We flew the same platform and the same sensor in 2021 to provide comparative data containing 3 years of change. We used ground control and we achieved high levels of auto-rectification accuracy. Although we said we weren't going to report those in this talk, they are in the report. I think they are important here. The ground resolution for both data sets was 2.1 centimeters, and the accuracy of correction was equal to or better than the size of a pixel in all dimensions. So as far as we can tell, these are comparable data sets. And these are the 2 elevation models, again clipped to the same extent for direct comparison. And yes, this is Birch and Lee again, where we undertook the thermal analysis. We'd walked up the hill with the equipment, but it seemed folly not to collect more data on the same day. Now the minimum and the maximum values of elevation in 2021 were higher than those in 2018, ranging from between 9 to 16 centimetres, which is interesting. Firstly, we undertook a simple DEM analysis to assess the variation. We simply subtracted the 2018 data from the 2021 data. And this is the difference, which raises a number of concerns. Firstly, a reduction in elevation of up to 1 metre and an increase of elevation up to 1.25 metres is evident. That's a range of 2.25 metres of change. Of additional concern are distinct zones of change across the data. In the northerly and southerly sections of the model, the data appear to show a general decrease in elevation. Yet in the central portion, the data appear to show a general increase in elevation. Now, they say you should leave the best till last, but unfortunately, this is not a systematic shift in the data, and there's not a lot we can do with the analysis. We could perhaps focus on a very small area, but the aim here was to test landscape scale change. So this component we know needs further work, and we have identified a series of approaches to address this, and we're currently working on those. And I'll finish on a pretty picture, and I'll hand you back to Adrian for a summation.
Well, thanks, Ben. I think we've both said rather a lot now. And well done to those of you who managed to stay awake. And for those of you who didn't and actually dozed off a bit, just woken back up again, is a brief summary. Firstly, it's probably unlikely that you're wanting to monitor for fun, something to do on a wet Sunday afternoon, say. It's more likely to be part of a specific project and funding round, and monitoring is a key part of proving how well you spent their money. So this cannot really be treated casually, like playing with model aeroplanes, or even real ones. I would suggest it's a professional obligation that reflects on your organisation. So just because someone has said excitedly at a meeting, oh, let's just use remote sensing, or let's buy UAV, or equally because someone knocks on the door selling UAV or MAV services, doesn't make your monitoring remote sensing. It simply doesn't, because the flying and the getting pictures isn't remote sensing, it's the least part of it. Rather, it's an integrated, ongoing program involving a lot of planning, debate about typologies, a very significant period of field data collection, alarming amounts of data verification and cleaning time, computer image analysis, error checking, statistics, and then the data you want is there. Just sort of as a humorous aside perhaps, just want to stress this, do not assume that what you need to do specifically can actually be done. Some users, for example, have told me they assumed there was something like a universal algorithm for vegetation, a sort of directory of spectral signatures for all plants. Yeah, if only it was. It really isn't. Sorry about that. Maybe they got confused with NDVI, I don't know. But let me say at the moment, there's no guaranteed off-the-shelf solutions for things that you want to do. Now, when this project started, we didn't even have a shelf. So this project changed somewhat from its original naive aspirations. Now, we were very lucky here. We started off with a bit of DIY, knocking up a few shelves first, for example. And here we were tremendously lucky to have partnered with MFFP, because they rapidly realised this too and reorientated the project. And more to the point, because this project was long enough to enable us to try stuff, try again, and learn. Had it been one of those more usual few months or year projects, well, it wouldn't have been so good. And after an awful lot of learning by both us and MFFP, we have got to a perfectly workable integrated solution. Now it is off the shelf. Now we know what can be done, and rather more importantly, what cannot be done, and how to accommodate these realities into a monitoring plan. And also, please, don't just make the mistake that any sort of remote sensing replaces fieldwork commitment. You'll have to commit to a lot of it. It is not either or, it is both. So in summary, what can you do? Well, we know this now, if you use 5 cm MAV imagery, simple classification will allow you to map the main upland players as species, e.g. heather, back, stereo, millennium, etc., as well as bracken, to accuracies that allow monitoring. Now with a caution here that perhaps this ought to be limited to a single round, i.e. before and after, as errors are considered multiplicative, and I can't say that word. And if you don't know what it means either, please ask at the end. It's a critical consideration in monitoring or change detection by remote sensing. There's also, of course, here a point about rare species. These are problematical for most survey approaches, and it's no different here. We simply did not get enough samples to allow classification for most of the minor players in the landscape. Now, if you map to functionally important groups, from a conservation perspective that is, this can overcome that constraint somewhat, and you get much higher accuracies. Now, as a group, this instantly also included sphagnales, which was a key target here for MFFP. These map to over 57% accuracy. Now, I actually don't think you can expect much better, given that you're flying overhead at, say, roughly 7,000 feet and at several hundred knots, and mapping sphagnum over 11 square kilometres. That is remote sensing. It's not going to be perfect. But how long would that take by hand? And more to the point, unless you crawled on hands and knees over every square metre, consider how many patches of sphagnum you might miss. We have to interpret the remote sensing accuracy here with the limits of hand survey. And also, of course, on all counts, it's much superior to, say, NBC. Now, other conservation targets that were really important here, such as exposed peat surface, bare peat, minerals such like, these are trivial to map at high accuracy to monitoring change. Now, of course, the point here is that both maps can be combined, giving a scalable product. You have higher accuracies with lower taxonomic differentiation, and vice versa. And of course, all of this is without that hidden problem, that hidden inaccuracy arising from ambiguity in field data. It is all based on species. Now, I'm sure someone will spot in the title again that the report's got UAV in it. And they're all the rage now because they're seen to be cheap. And hey, who doesn't want to fly model aeroplanes, especially on a nice sunny day with a coffee and sarnie in hand? So can you use them? Well, this is great really. After 4 years, I can definitively state, maybe. Yeah, you heard it here first, folks. Maybe. That in principle, they could provide resolutions matching those we used from UAV. And as you saw earlier in phase 1, the accuracies achieved were not that far short from those in phase 3, in the one place we could check at least. But that possibility has to be caveated, and it's a big caveat really. Even if you can do this, given our experience, you can only do so where you can keep the imaging time to perhaps around 30 minutes or less. Now, given the very small footprints of the tiny sensors UAVs carry, this directly translates into smaller areas, hectares rather than square kilometres. Now, it's a challenge here really. If you think that statement is wrong and unsubstantiated because our experience was limited to just really 1 or 2 years, then please feel free to think that. I've no particular axe to grind here. I'll classify any imagery you want to send to me. It is just that we tried it over large areas and experienced a lot of issues. If you want to use a UAV professionally to produce scientifically supportable data over large areas, especially to report back to big funders, and not just to create pretty pictures and prettier claims, then I look forward to being, proven wrong with some startling accuracy estimates. I would love that. It would be wonderful. All I will say further on this is that we now know what is likely achievable using 5 centimetre MAV and how to go about it. And if you read the report, so will you. This is as open source as it gets. We're not selling unique selling point. We're not bent over trying to hide some arcane knowledge. We haven't painted it a secret source full of salt and colouring. That would have been an anathema to the ethos of this project at the start. Yes, we're happy to do such work for you if you insist. Please send it to us. But we use methods that anyone in principle can deploy. So what about EO then? Well, I think you can probably get a clue for the answer here, what I'm going to say. Yes, we were mapping species using extremely high resolution 5 centimetre imagery. And the reason for this was to bypass the unavoidable ambiguities in all habitat and community descriptors. So the field approach wasn't designed for 1 to 2 megapixels of the latest satellite sensors. So yes, it's problematical there. Right now, I don't see how you could use EO for species mapping in diverse upland habitats of smaller plants without going backwards and picking some nebulous field criteria like dense heather, less dense heather, heather mosaic, all that rubbish all over again. Or for that matter, phase 1 habitats or NBC, all of which I'm sure will fail. Technology, especially the sensors, have moved on. We don't need to do that anymore. We can work with what we know and we know we can identify, and that is species. Perhaps we should just move on and stay there, so to speak. Let's briefly look at the opposite, things you're unlikely to be able to achieve, and I think this might annoy some people, more than I have already perhaps. Firstly, thermal. Now, there's a lot of claims out there being made. I keep hearing, oh yes, you can measure moisture using thermal and all sorts of similar sort of verbal reports. Let's just recapitulate what Ben has pointed out. There is simply no absolute link between temperature and moisture, and nobody has ever claimed there is, because there isn't. You cannot measure temperature from a UAV and know the soil moisture. You cannot say, haha, that patch contains 82% moisture by mass or by volume, whatever. That bit over there only 47%. Nope. End of it. You can't do that. The principle I think people are talking about is a simple one, of course, that a wet substrate is more thermally buffered than a dry one because water's got a very high heat capacity. So wet peat will both warm and then cool slower compared to dry bits. But all you can do with a thermal sensor is to measure relative differences. Now these constantly change depending on when you do it, because the moisture itself isn't causing the heat. That's insolation. And insolation varies according to topology and aspect, and of course shading by vegetation, weather of time of day, such like. So you cannot realistically even compare through time, because all the drivers of the heat input will vary. And then we get to another little elephant, maybe it's a big one, I don't know, maybe it's grown up now. No one has ever suggested the temperature of vegetation varies with moisture. I mean, this doesn't make sense. Either the plant itself or the peat it is growing in. So the effect is only valid, even in principle, on bare peat surfaces. And we kind of hope there isn't a lot of that on your bog. What you can do is indicate wetter and drier bits of any exposed peat, once you've managed to factor in changes in insulation. If you want to know what that actually translates to as a moisture measurement, you'll have to take soil samples every time, which possibly negates the effort of flying the sensor in the first place. And of course the great thing about going in from field sample is that while you're doing so, you can kind of look under the vegetation too and get some samples down there, because your thermal sensor isn't going to tell you anything about that. So I think if you manage a totally level and flat patch of bare peat, a UAV thermal sensor will tell you the wetter bits from the drier bits, but it won't still tell you how wet or how dry. Let's look quickly at something based on more sound principles, determining erosion by measuring differences in topology using very high resolution UAV derived dams. This is all completely sound and well demonstrated by, for example, Glendale 2017. No debate there. It'll be perfectly possible to create 3D models and compare them, with a little fiddling maybe, but I remain convinced this technology is ready to deploy. Before you jump up and down with excitement though, I suggest that you consider the nature of Glendale's study. It considered changes in small areas of creeks or erosion channels in the peat. And it works, that's to be expected. It doesn't mean you can scale it automatically to work over large and flatter areas at the scale of square kilometres. Because here again we run into the issues of vegetation. And that's probably going to stymie large area DEM comparisons because, well, plants grow and they're going to senesce. Now, vegetative areas were excluded in the Glendale study on those grounds, something that would make it irrelevant to large areas of bog and upland moorland. So I think probably best to say that currently the application of this approach over large areas for monitoring moorland rather than specific creeks is still an unproven case in point. So is it all despair? Should we be negative about remote sensing? You know, a lot of the past 90 minutes or so might lead you to believe that. Well, I don't think we should despair at all. Consider this. If you want quantitative data on vegetation abundance, which you will need to monitor change, the only conventional route is quadrat sampling. I repeat the word there, sampling. Now this gives you an estimate, an average say, and you can calculate your confidence limits on that average. So for example, you know, your project area is covered with 15% millennia. You get a confidence interval of maybe 7 to 23%. And this means you're 95% confident that the actual figure lies within that range because you sampled. You don't know exactly, you sampled, so you know within a range. Let's consider remote sensing. This doesn't sample. It surveys every square metre, well in this case 0.025 square metres, and tells you exactly how much of it thinks is on your side. But it cannot do it perfectly. There is an error in the classification. So this method will give you an estimate of how much there is, with a confidence limit on that number based on the inaccuracy. In my mind, there's functionally no difference. So it isn't gloom at all, I think. And of course, with remote sensing, you get a map of where things are as well, something you don't get with quadrat sampling. Right, now even I've grown bored on my own voice. I didn't think it was possible, but apparently it is. So in time-honoured tradition, I think I must say, with that, back to the studio. In the meantime, the report can be found at the link here. I'm not going to read all that out, it's a bit complicated, I'm bound to get it wrong. And any other questions you have, please try contact@coloptrix.com. Thank you. Do we have any questions? Dermot, can we hand back to you and let you handle the 10 million questions I'm sure this is created?
Did you want me to do that, Dermot?
Yes, please, if you don't mind, Tia.
So, and now because people are adding, it's moving where I was. So there were two from Christoph. I think the first one's been answered because that was about aggregating species. But the first question asked was, is there an unclassified class, or did you attempt to classify the whole image?
Yeah, there's, well, okay, we can both answer that. I will jump in and swap each other. No, we're using a max list, which means that it will always assign pixels to a class. If you use something else, non-parametric and such like, you will get, or you can get unclassified pixels. You probably get a higher accuracy, but you get an unclassified class, as you say. In this case with max lick, you don't get that. It assigns, funnily enough, the maximum likelihood class to the pixel that it's found.
Okay, there was also then some discussion around dead header, the dead header category. And there was discussion that went on in the chat, but I think probably the question that came out of that was would grouping all header together improve or reduce the accuracy? That was from Chris Wood.
Spooky. Yeah, hi Chris. Well, actual fact, that was what we've done. We had done it in phase. We had done it earlier because the class. Okay, here's where some of the rushing around and trying to compress things to try and fit 4 years of work into a couple of hours as a problem. And usually our map cleaner class, when we mapped it as species, in fact, generally speaking, included senesced, flowering, and vegetative classes grouped as one. We've mapped them separately because they'll have different spectral signatures, and then we pool them into one combined class with an average accuracy across those three classes. So the dead one was problematical, and it's the same with burns. 1 or 2 of the sites were marked as burnt heather. Now, yeah, burnt heather, we know it was heather, and we know if we leave it and we come back, it will become heather. But you can't really you only classify what you can see in the picture on the day. And the dead header class did map in that particular picture, a very, very tiny subset of kinder that I showed you. It did map quite abundantly in there, and I just simply want to point that out to you. It wasn't necessarily a problem with the entire area, if that makes sense. I haven't answered that question, have I? That's one for later when the bar's open.
Thank you. Another one from Christoph. So this is to do with peat moisture. Did you look at the relationship between soil moisture versus temperature change between the two flights?
Okay.
We haven't looked at the temperature change. We certainly can. I'm not entirely sure what it might tell us. Because the biggest thing about the temperature change, I think, is the aspect. It's very, very clear that depending on where your sun angle is, that has a significant impact on the temperature that you're receiving. And this, I think, is a problem moving forward in terms of using it. Yes, we've only sampled, we sampled bare peat because it seemed obvious at the time. It was only afterwards we then thought, actually, this isn't necessarily what we're interested in. I suppose what we're trying to do is get information on where your water is across large areas. Now, this doesn't tell us the water table. I mean, I can certainly have a look at this, the temperature change, but I'm just wondering, unless you have a thought, I mean, we're interested to hear from you if you think there's something in that we're missing, that you think that's telling us something.
I'm no great expert, but
probably no more than me. Oh no, I didn't say that.
I assume that the water would buffer the temperature change to some extent. So the wetter it is, that'd be my hypothesis going in, the less the temperature changes during the day. And on the aspect point, yeah, I totally agree. I guess, can you add the aspect into the model to correct for that, I guess. But yeah, I'm also wondering whether you're not just if you go beyond bare peat, you're not just reading the vegetation temperature, which won't be so affected by soil wetness.
That's right. I think that is a problem. Yeah.
Sorry,
now I did collect some data from the flow country. Now this does show what you're saying, and it was we were flying for about half an hour, and we'd been waiting all day for the sun to come out, and it didn't. It was cloudy all day. So the first 15 minutes of the flight was with cloud cover, and then the sun suddenly came out, and the last 15 minutes was in sunshine, and it was over a pool system, and what you could see in that 15 minutes was that the pools of water absolutely buffered the temperature, but the temperature of the vegetation shot up 3-4 degrees. So there is a potential for the soil moisture to buffer it.
I can, Ben. I think the problem here is that I think we're chasing something which doesn't really exist. Is that you want to measure moisture in the soil because you want to see whether your re-wetting is succeeding and everything else. Now, nobody's ever claimed, no matter it's part of the planet or any other planet, as far as I'm aware, that the temperature of a plant is dependent or is on its moisture content. And it certainly isn't going to tell you anything about the moisture underneath the plant. So many factors determine soil moisture within vegetation that are over and above the temperature. So as soon as you only do this on your bare peat, and not bare peat with water in it, so to speak, there's also a bit of a problem. So why, I know people want to do this, but why, I didn't listen to the summary, I cut that bit out. If you're only going to derive information on 1% less than that, probably, hopefully, on your bog, it isn't going to help you. So that's my feeling. It's just that, yeah, theoretically, it's going to be a link, obviously. It's underground moles. I mean, definitely, I agree. Let's get some moles involved. I mean, should we move on? Because frankly, I think even if we had debate about it here, we're not finding a tool which is useful because we can't apply it in the environment we want to apply it.
Yeah, we've got quite a few more questions, so I'll move on to the next one, and perhaps we can pick up any extra discussions afterwards. So a question for Ben, and this is about the erosion accumulation work. Any ideas for the reasons for the elevation changes?
Yes, but I'm a bit cautious of saying why, because we're testing a whole load of reasons. I think the important thing to draw from it is that if you undertake what we would see as probably a conventional monitoring program, you go out, you set up targets, you get the position, you correct your data, you go back 3 years, same process. There's something within that, there are some errors within the system that are going to cause non-systematic changes. Now, I say we haven't fully tested this, so I don't think there's any point in you saying, oh, it's this, that, and that, and then coming back next week and saying, actually, it wasn't that. In fact, we don't still know what it is. But yes, I don't know whether that really helps you. So yes, we do have an idea, but I'm going to say I'm a bit cautious about telling you what it might not be. Sorry, does that help you vaguely?
Maybe that's something we can share in the future when we're a bit clearer on it. So next question from Kath Longdon. Interested to know if the spectral recognition changes in the season. So would Nardus be easier to see in winter, as is Molinia and common cotton grass? And do we therefore need to fly photos across different areas at different times of year, depending on the species present?
Yeah, it's a good point. I mean, we haven't covered this 2 hours. UAVs give you a potential opportunity to fly multi-temporal flights, I suppose. You can fly different times of the year. And you can use the change in spectra to improve your classification. Because, yes, I made the point very briefly earlier, all plants are green in essence, and all the differentiation has occurred in one dimension, which is a real problem. But when you start factoring in flowers, changing through time, some plants don't senesce in color, like for example, heather doesn't change an awful lot through under it's flowering or dead or burnt, whereas other species show green and then they senesce during the winter. So you can use that quite rightly, and you've picked it up there, that that would allow you to improve classification no end. Absolutely. And that would have formed an early part of the UAV approach that we probably would have adopted. Multi-temporal comparator analysis is a very, very useful way of improving spectral classification. Absolutely. Unfortunately, owing to the fact that we moved away from UAVs to MAVs, and MAVs are wonderful, and yes, wow, we'd have loved 7 flights with an MAV. It would have cost a lot of money. MAVs are more expensive if you're going to do more than 1 or 2 flights than flying your own UAV. So yes, had the project been different over a much smaller area, just for research, to test something out, we would have gone for multi-temporal UAV thing. We were being asked to map over 11 square kilometers, so we didn't have the ability to go and go forward and do that. But you are absolutely right. It would improve classification. I'm convinced it would, but I speak without any evidence in this particular case.
Can I just ask a question then, like on that same topic? Would you not then be reintroducing the issue of shadow if we're flying at different times of year?
Yeah, you do. Yeah, yeah. These are all. I mean, it's not magic. There is no magical wand to wave here. So yes, you will introduce other problems, and you, try and find a solution to that. It's been used mainly in things like cropping and that sort of stuff. Actually, it's been used quite extensively in detecting opium crops in a certain part of the world, Cranfield, because you can detect harvest and post-harvest. So it has an advantage, but you're right, it brings a suite of other issues with it. Yeah.
Great, thank you. Next one, could you tell where the lost millennia went? So I think that one's asking what species the millennia was confused with.
That will be in the error tables. Off my head, no.
Page 76 or something.
Page 472, yeah, paragraphs. It will be in there. I mean, the confusion table, the spectral confusion table, show you what species are being confused with. So yes, that's all in there. From memory, I have no idea. Ben's probably desperately looking up to find out now. Always looking out the window at the dog.
It does. There is a range. I mean, what we haven't really been able to sort of cover as well is, although we have said there are 5 different sites, they are all slightly different. So although actually we've mapped the whole lot, one of these sites, which is Moss Moor, is, I think it's referred to as Millennia Moor sometimes because it's very millennia dominated. And from memory there, it was Erosion vaginatum that it was been getting confused with. And I think that's one thing. I don't think we could say, oh, it's only going to be confused with this. I think there is going to be phenological variation on your sites. And at some places you might be confused with cyclone. At other places it might be confused with trichophorum. And there are lots of error tables, so you'll be able to find what it's confused with where. I don't think it's going to be helpful going through 22 error tables now.
Was that Amanda? Did you say it was Amanda asked the question? What I can say is, Amanda, yes, we do know what it got confused with. Pass on.
Next question.
It's not able to tell you right now.
Did you or could you factor in change in the structure of vegetation? This has multiple applications for habitat restoration and management.
Yeah, again, in principle, you can. I think the problem here, yes, of course you can. The more things you factor in, the better will be, in principle, your classification. So if you can include texture, the problem including texture is that you can only do that within multi-pixel aggregations. So what it's going to try and tell you, you're going to try and spot texture by looking at variants in the pixels of the same species in the same kind of general locale. So it is a useful tool, and it's been used in the past quite extensively with Earth observation. But you're talking of looking at big, massively big stands, you know, like a big arable field somewhere in the middle of nowhere or middle of America. Doing it on species has not been done, so there's a project for you. It possibly would improve, but you don't see texture within the pixel. You see texture between the pixels. That's the kind of metaphor. That's the kind of surrogate that you're looking for, is variation within a pixel. That as we are trying to align 5 centimeter pixels with a field sample, we have to allow some variance within that, just to allow for topological differences in the adjustment or whatever. So it would be hard in this case, and using the protocol we've used. I like the idea. I'm not poo-pooing it at all, if that's a word. I think there's always lots of experimental projects, and there are thousands of experimental projects out there where people spend 6 months or a year or 18 months or even an entire PhD reclassifying, trying something different on a particular image. But when you try to apply it a second time over a different site, it doesn't work in the same way if you apply it. So we were tasked with trying to make something, I won't say crude, we were tasked with trying to manufacture a reliable vehicle for reliable monitoring over very large areas in the uplands, not a finely polished something. So yeah, it would work, I'm sure, and I'm sure it will do something for you. We just didn't test that because that wasn't in our kind of remit, if you like. And that probably sounds like a terrible answer, but we were trying to head as fast as we could towards a dependable large area survey process. So I'll shut up on that because I've just been going around in circles.
So there are 3 more questions. I'm conscious that we're at 4 o'clock, but if people are happy to stay on just for a few more minutes, and hopefully if you ask that question, you are still on here. So the next one is, can near infrared be used for soil moisture? I guess that's one for Ben.
Well, water as a class is one of the most accurate, should be one of the most accurate classes. So near infrared is very good for mapping open water bodies. How well it's going to map soil moisture, I don't know, because bare peat has a similar response to water anyway. I've not seen anybody use near infrared for mapping soil moisture, unless somebody here has used it. I think it will show you where bare peat and water are, but I don't think it will tell you moisture. It's my interpretation. Happy to be told by someone here, actually, yes, we've used it. So, no, in short.
I think it would apply the same thing. You only be able to do it on the areas of bare peat or on the areas of standing water, as opposed to where the vegetation is. I saw a question on sphagnum come up earlier about, can you map sphagnum under vegetation? Is that one that's going to come up to you?
That's the next one.
Wow. Look, I've caught up with the 10-second delay there. I'm even much ahead. Oh. Okay. Yeah, a very valid point. When you're mapping Earth observation, you are mapping what can be seen from, orbit, sky, whatever. You cannot tell what's underneath. And that is a problem. So you know that you're always going to see what's on top. Nothing you can do to avoid that. We were hoping we could do something with that with UAVs, because they give you so many multiple variable views that you can see under some vegetation. But like I say, that development side of things, we were never going to do 11 square kilometers using UAVs. So we moved away from that. So your answer to the question is, no, you can't see under the plant or under the tree or anything else. I'm sorry about that. It'd be great if you could.
Last question then. How confident are you that the UAV elevation maps were truly DTMs rather than DSMs? And could the elevation differences you observe partially relate to vegetation growth and decline, not ground motion?
Yeah,
right.
Thank you, Ben.
Yeah, so that's probably, I should have been clearer on the slide. They were DSMs. So they did include the vegetation, and you're absolutely right. And within the data, certainly, some shrubs looked notably higher. Now, it is entirely possible that those changes were a growth of the plant, but it was the whole fact that there were 3 zones. And given that that's a DSM, I mean, it's not impossible that the vegetation at the top and the bottom all shrunk and the vegetation in the middle grew, but there's a non-systematic variation. It's about the way that data are processed rather than collected. That is what's causing an issue. So did that answer the question? Yeah, right. So there were DSMs. So some of it could be vegetation height. Partially, yes, but I don't think it's ground motion. I think, again, I know people do map and are interested in bog breathing. I don't think that's what we're seeing. It's entirely possible that some bog breathing happened. I say it's more about the processing that is what we're working on, and hopefully we'll be able to. I don't think we've got another report to give to you here, but I think we'd certainly have to be able to come back and update and say, right, this is an approach now. These are the 3 or 4 things that you need to factor in when you do the first one, and this is what you then need to do with any subsequent flights.
Thank you all. And everything I said was always meant in a kind of collegiate manner, as opposed to a confrontational one. Please don't be offended by what I've said. So, yeah, thank you all. Thank you all for coming.
And thank you very much, everybody, for attending. We'll be sending out the links to the presentation that I've recorded. And yeah, so thank you very much, everybody, for being with us today. And thank you very much, Adrian and Tia and Ben as well. So thank you very much for a very enlightening presentation. And speak to you all soon. Thank you. Bye.
Thanks a lot. Cheers then. Bye-bye.
Cheers.
Bye.
Thank you all. Bye.